Now let's take a look into an example. So if we go back to our simple example of an exponential decay signal, and now we'll show how to implement it. So we'll just need a system with a pole at the position P. And if we look in the equations, difference equations before, we obtain by setting the P0 to 1 and A1 here equals to P. So then we will have X, this is 1, so this is P here, Y of n, and there is a delay here by Z to the power, so this delay by one sample, and here A1 is equal to P, and then we will have this equation here. So this is 1, so this is the P0 times X of n plus P, this is A1 equals to P, and the delayed version of the input by one sample. So here you can see that X of n is the unit pulse. If the X of n is the unit pulse, the output is the exponential decaying sequence, like we've seen before, which is an infinitely long impulse response, hence the name infinite impulse response. We can also see this equation in the form of a block diagram. So we have our input and we have our output. There is a delay by one sample, so here we have y of n minus 1, and we'll multiply with a1 equals to p, so this is equals to p, then here we have p times y of n minus 1, so we have this part here, this addition, and this part here, and this is our output. So you can also compare with the Python implementation block diagram on the case that p0 is equal to 1 and a1 is equal to p. So if we take this and we go to the z domain by applying the z transform, we'll have that the y, capital Y of z, will be the capital Y of the z transform of the input signal plus p, this is our pole, times z to the power of minus 1 times y of z. And from here we can have our transfer function, so we're dividing the output by the input, and we have this 1 divided by 1 minus p times z to the power of minus 1. So in this structure we can see now the feedback loop. So observe that this is the same as the z transform of our exponential series we've seen before. This means that when we transform this back to the time domain, we will obtain an exponential function, which is the filter's impulse response. So this confirms what we just saw by using an impulse response in the time domain for our filter. So the result of the inverse z transform of our transfer function is in fact 1 with this p to the power of 0, p to the power of 1, to the power of 2, and p to the power of 3, and so on.